Am I audible to you, students?
Yes, ma'am.
Yes, ma'am.
Okay, 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 fine, fine. Well, recall that yesterday we were discussing about non-homogeneous linear recurrence relations with constant coefficients. So just you remember this non-homogeneous linear recurrence relations relation with constant coefficients. We are looking into this. Well, so this I have already told that this is of the form. You just remember this B0 an B1 n an minus 1 like this. Bk a n minus k is equal to some function of n. Right, it is non-homogeneous means fn is not a zero function. I mean, this is not equal to 0. So that is why the non-homogeneous. And then its solution, I have told you that its general solution will be consist of two parts. So if I mean the general solution that an is actually this is general solution an is consist of two parts. One is this homogeneous from this homogeneous part, and the other one is particular integral ANP. So this is, I mean, ANH is the general solution of the homogeneous part. You understand, by this homogeneous part, and ANP is a particular solution. This is a particular solution. Particular solution. So already we have discussed the method of finding ANH, the general solution of homogeneous part. Then how to obtain this ANP, a particular solution? So one may get by several ways, but here we shall discuss the method of undetermined coefficients. So this method of undetermined coefficient to find particular solution. So this method of undetermined coefficients to obtain the particular solution, obtain a particular solution A and P. So in this method of undetermined coefficients, actually, what we do, I mean, some, forms are there. I mean, I mean, if you have done this, that differential equations we have solved by using method of undetermined coefficients, then it will be, I mean, easy for you that you can recall how we have done the method. So this, I mean, what we do is basically for this particular solution, actually if depending on its form, that what kind of this function, I mean this fn is, what kind of this function fn here in the right hand side, this fn, for depending on the kind of function of this fn, we formulate a particular solution. Okay, we formulate a particular solution, and that will be depending on some coefficients, I mean some constants, some unknowns. Okay, some unknown, some constants will be involved in this particular solution, and that form of this particular solution will be I mean determined, or that form will be constructed depending on this function fn. What kind of this function fn? Accordingly, we have to select this a and p uh, in terms of some unknown, some constants, actually some constants, and those constants will be determined by substituting this assumed, that this we have considered this assumed particular solution in the given recurrence relation. In the given recurrence relation, we will substitute that our that assumed this particular solution. This is of that what form, this form of this particular solution I have told you, that will get depending on the different kind of functions fn. So once we assume this particular solution, provided that some unknown, some constants will be involved, and those constants will be obtained by substituting this, assumed particular solution in this equation, in this, recurrence relation, in this recurrence relation, and those unknowns will be determined. Fine. So then, for what kind of functions fn, how should we select this particular solution? How should we select this particular solution? So there is a table actually that for different kind of functions fn, different kind of particular solution. What kind of this, what form of this particular solution you are going to assume, so that it will work out and you will be able to find out its value. So I'll write some of them, and of course we'll deal these kind of functions fn only, and let me write down this. So here I will go to the next page. Okay, well, so if this function fn, this table I'll form, okay. So here this function fn, and then the particular, so solution a and p, what we should select. Suppose fn is a constant. Okay, fn is a constant. Okay, no need of writing this straight. I'll write that a constant. Select this eraser. So this fn is a constant. Is a constant. Any constant actually, say c is a constant c. Then for a and p, we shall select not necessarily the same constant c. Okay, we shall use this notation, say a. A is a constant. A constant. Because we have to determine this value of this constant a by substituting. And then say this is first form, then this second form of this function fn. Fn is some constant time this n to the power t. Okay, this n is involved actually that in that recurrence relation, same n. if it is n to the power t, and in this case actually we'll have the two subcases. I mean, it is Fn is c into n to the power t, and one is not, I mean, provided that this one is not a characteristic root. It is not a characteristic root, not a characteristic root. And you understand why this characteristic root. One is not a characteristic root. Then in that case, we have to substitute for this particular solution is a, I mean this a t n to the power t plus the same t in the left hand side. This t is coming from there. Okay, n to the power t, that power is there. And a t minus 1 n to the power t minus 1, we have to substitute as a polynomial for this particular solution. A1 n plus a0, and these are all constants actually. This a0 to at are constant. These are constants. And if this is, I mean, if one is a characteristic root, so the same form, and one is a characteristic root. Here, one is a characteristic root of multiplicity m, of multiplicity n. I mean repeated root, multiplicity m. I mean one is a characteristic root with multiplicity m. So then we have to substitute this by n to the power m and this full, I mean the same polynomial here, a t n to the power t plus a t minus 1 n to the power t minus 1 and this a0. This. So then next, if this function fn is of the form, I mean this form constant time r to the power n. R is any real number. Okay, here R is any real number. R is any real number. In the previous case, we have taken that n actually particularly. In that second case, we have taken this n particularly. That particular, I mean that is an integer actually. And here R can be any real number. So here also we'll have that two cases that okay, this here you can say that this is a first case and this is, I mean, sub case, second sub case. So here also we will take our sub case is that R is not a root of the characteristic equation. This R is not a characteristic root, not a characteristic root. So in that case, we have to substitute this a r to the power n, a r to the power n. And then second case, second sub case, this r is a root of characteristic root, r is a characteristic root of multiplicity m, of multiplicity m. So in that case, we substitute this particular solution by a into this n to the power m and r to the power n. Here this A, I mean the capital A, I have written that is a constant. A is a constant. That actually we determine by substituting this particular solution. By substituting the particular solution in the given recurrence relation, we substitute and obtain the values of this constant. Okay. Moreover, I mean, there are, you'll find actually that in case of differential equation also that some big table, I mean, for different kind of this function fn, the different values and all that. So similarly here also, those values for different values of function fn particular solution what one selects, that is also there. And here I am not writing others because we'll deal with problems for which this fn will be in these forms only. Okay, but in general there are some more actually. This bigger table is there. And one more thing I will tell you that this if fn is, say for example, fn is the not only it is a constant or not only it is this form that constant time n to the power t or this power of rn, if it is sum of these, if this function fn may be that some constant time, I mean c plus some d times rn, maybe sum of 1 and 2, 1 and 3 will be there. So accordingly, you have to select the particular solution that sum of, sum of particular solutions in those two forms actually. Okay. I'll give one example and then explain this method. Okay, keep this table in mind. We'll therefore look at this example. For this example, let us discuss this example. Suppose we'll solve this recurrence relation. Solve the recurrence relation. It is a n plus, it is given like this. Oh, okay. Fine. It is given in this form. Okay, let me tell you that it is given in this form: an minus 8 an minus 1 plus 16a n minus 2 is equal to, this is given 8 times 5 to the power n plus 6 into 4 to the power n. Suppose it is given like this. Okay. And this value of a0 together with this, okay, here n is greater than or equal to 2, and the value of a0 here, which is say 12, and a1 is equal to 5. This is how it is given. Well, so then this is a non-homogeneous recurrence relation. We have to find the first of all general solution of this homogeneous part. Okay, this is the first case. So the general solution, to find this general solution of this homogeneous part, we have to write down the characteristic equation of the homogeneous part actually. The homogeneous part, so that is x squared minus 8 plus 8x plus 16 is equal to 0. X square minus 8x plus 16 equal to 0. So what are the roots over here? Roots are characteristic. What are the characteristic roots? What are the characteristic roots?
4, 4.
4 and 4.
4 and 4, right? Yes, 4 and 4. So these are the characteristic roots. So I mean characteristic root is only one, that is 4 with multiplicity 2. With multiplicity 2. So therefore, I mean we can write this general solution of course with a constant. What will be the general solution for the homogeneous part? For this homogeneous part, the general solution will be here some constant time. Okay, let us take some constant time. You know that 4 to the power n plus another constant, that b into n, 4 to the power n. This is how the, okay, multiplicity is 2. So therefore, we will have the general solution like this. A, B, they are constant. Okay, they are constant, that we shall determine. Okay, so now the general solution is like this. We shall determine this constants A and B at the end only. Fine. Okay, so then this, I mean we shall consider the particular solution. What will be particular solution? For that particular solution, look at this Fn is given here, that 8 into 5, it is of this form, 5 to the power n plus 6 into 4 to the power n. This is what the Fn is given. So we are, I mean this function Fn is in which form? We are in which form of this function? Fn. Okay, we are in which form? Just to look at.
Third.
Yes. Constant. Yeah, this is a third. Okay, third one. Okay, but this first term 5 is not a characteristic root, whereas this second term 4 is a characteristic root. So therefore, you tell me what I have told you. This is actually both this third I and double I. Okay, third I and double I form, right? Third I and double I. So therefore, the particular solution we shall consider is, so this we consider this particular, consider the particular solution A and P is of what form? This 3I. First term will be 3I. Means that is we are some constant time 5 to the power n. Constant time this 5 to the power n. This C is a constant that will determine. And second term is this 3 I double I. So that is because 4 is a characteristic root of multiplicity 2. So therefore we have to write some constant d times n square and this 4 to the power n. Right, 4 to the power n. It is fine. The particular solution we consider like this. The particular solution will be considered like this. Okay, this will come from 3I and double I. Now we take this particular solution and substitute in the recurrence relation. Okay, substitute in the recurrence relation. So in the recurrence relation, if we substitute, then what do we get? Okay, recurrence relation is, ours is this an. Okay, fine. An means we'll substitute this in equation 1, say suppose 1. So now you put this a n p in E1. So a n, for a n we shall consider this is c 5 to the power n, that is a n, plus d n square 4 to the power n. This is a n, and minus 8 times that n minus 1, c 5 to the power n minus 1 plus d n minus 1 whole square into 4 to the power 4 to the power n minus 1. Okay, so this is for a n minus 1. Then 16 times a n minus 2. A n minus 2 means here c into 5 to the power n minus 2 plus d n minus 2 whole square into 4 to the power n minus 2. Okay. Well, I could have put a curly bracket. So this is equal to, we have 8 into 5 to the power n plus 6 into 4 to the power n. So from this equation, I mean in this equation, what we'll do, in the left hand side, we will collect the coefficient of 5 to the power n. Okay, we will collect the coefficient of 5 to the power n and 4 to the power n, and then we'll compare with right hand side. So left hand side, the coefficient of 5 to the power n and coefficient of 4 to the power n, and then compare with this coefficients in the right hand side. You have to equate, and then we obtain the values of C and D. So tell me quickly here, this example that I was solving, and what will be the coefficient of, you have to calculate and tell me. This I was working. So here, what will be the coefficient of, okay, this comparing this, okay, that tell me what will be the coefficient of 5 to the power n, and then here what will be the coefficient of 4 to the power n. You have to tell me. So once we'll, obtain in the left hand side, then right hand side we are having this, and the coefficient what we will obtain here, that value, that will be equal to 8, and the second one, this one will be equal to 6, that is coefficient of 4 to the power n. Okay, so can you compute this and tell me what do you get here? This 5 to the power n means here I will get c. Okay, from here, and here 5 to the power n, if I take common means 5 to the power n, then I have to multiply by 5 also, that minus 8 c 5 to the power n minus 1. So here we get that c minus, okay, so that we have to divide, right? We have to divide by 5, 5 to the power n. So 8 by 5 c. Fine. From here we have taken this 5 to the power n common, so therefore I will get that. And from this third term, if I take this, okay, plus 16 by 25. Okay, and here C is there. Fine, that 5 to the power n I have taken common, so therefore I have to divide by this. It is all right. Okay, it is correct or not? You tell me. I am just
Yes, ma'am.
working. Huh? Okay.
Yes, ma'am.
Yeah, very good. So then you tell me the coefficient of 4 to the power n. 4 to the power n is here we are having d, here we are having this h, okay, okay, we are having this n square also fine. Well, so this 4 to the power n, that coefficient dn square, and then on the other side similarly we are having d, okay, 8 by 4, that 4 to the power n we are taking common. So then d n minus 1 whole square, and from this third term it is coming this 16 by 16, it is 1 only, and then dn minus 2 square, dn minus 2 square, okay, dn minus 2 square. Well, so this now if we compare the coefficients on both sides,
Ma'am, C equals to 200 and D equals to 3.
c equal to
200?
200.
200,
Yes,
Yes,
ma'am.
ma'am.
c equal to 200 you are getting, and d equal to
3.
3.
eh?
3.
D equal to 3.
3, okay. So now we obtain this C and D like this, in this fashion, okay. So therefore your particular solution A and P will be, particular solution A and P is A, okay, A and P, the particular solution was like this, we have substituted in this form. So therefore you have 200 into 5 to the power n plus d is 3 into n square 4 to the power n. Well, then this is particular solution we have got. So how do we get this homogeneous part? That general solution of the homogeneous part, we are still having the constants A and B here involved. We have to solve, we have to determine the constants A and B. So now what we will do is we shall write down this general solution A n, and then use your initial condition. Use your initial conditions. Okay, use your initial conditions. So here A n you write down as A into 4 to the power n plus B n into 4 to the power n plus the particular solution you are having this 200 into 5 to the power n plus this 3n square 4 to the power n. This is what the A n, together with this A and B are unknown. So for A and B we have to use our particular solution. So this A0 is equal to 12. A0 is equal to 12 here, and in the right hand side this is A and n is equal to 0, right? N equal to 0, so this term will be 0, and here you are getting 200, and this is 0, again this is 0. So therefore from here what do you get? This A is equal to, that you are getting minus, okay, that 12 minus 200 you are getting. So that is coming out to be your minus 188, 188. And then similarly we will obtain the other value, the value of B, the constant. So that you substitute the value of value of A1. A1 is 5. Okay, A1 is 5. So 5 is equal to A1. So you get, this is 4A plus n is equal to 1, 4b plus 200 into 5, 1000. And here you'll substitute 1. So this value is 12, right? N is equal to 1 here to substitute. So tell me what value you are getting, and value of A is, we have already obtained, that is minus 188. Here you simplify and tell me what is the value of B here.
Minus 255.
Minus
255.
255, is it correct? Actually, I haven't solved this completely.
55 by 4.
Huh?
Minus 255 divided by 4.
Divided by 4. Okay. You check actually, you verify this one. I am not sure that you calculate this value. Okay, once you obtain these values of A and B, that now we get our final answer is A and all these values you have to substitute. That A is minus 188 into 4 to the power n, and B you are saying this 255 by 4 into this 4, n is also there, right? N into 4 to the power n, and the rest we have already 200 into 5 to the power n plus 3n square 4 to the power n. This is what your final answer. Okay, so this is how we solve the non-homogeneous linear recurrence relations with constant coefficients. Well, you practice some problems, and we'll also discuss some more in the class later on tomorrow, and next week also fully. I mean, next week you'll have classes or not? You are having some test, but during this class hour, I think you will be having classes, I think, right? What is your situation? You are having some other test next week.
Yes, ma'am.
So what about next week classes then?
Ma'am, maybe we can discuss some light problems in the
Yeah. Some doubt. I'll take that doubt clearing classes and problem solving. I'll anyway not teach anything. Okay. So that I mean, you may join that for doubt clearing and problem solving on Wednesday and Thursday. Fine. So then next actually that in this combinatorics portion that I'll finish today, and maybe tomorrow one lecture I'll take 1 hour, and I'll finish this combinatorics portion. And after your this exams and all, maybe that from 15th onwards, 15th September, I'll start graph theory. Okay. So this combinatorics part, another interesting, I mean, two interesting things that the parameter or this is left, that is Starling number. So I shall just discuss about this Starling number. So Starling number. First we shall discuss, I'll tell you about Starling number of second kind. Starling number of second kind. Second kind is there means first kind is also come after this. First kind is also there. Well, second kind is there means first kind will also be there. And this Starling number of first kind, what it is? So it is like, just I'll tell you, it tells you about that partition of a set actually. It talks about that how many partitions of a set will be there. So what do you mean by partition of a set? What do you mean? I mean this Starling number of first kind or second kind, both are actually after this the name of Scottish mathematician actually. The Starling numbers are after this mathematician James Curtis, James Starling. He is a Scottish mathematician. Okay. James Stirling, his lifespan was 1692 to 1770. This was the lifetime of James Stirling. So this Stirling number of second kind, it tells about the partition of a set. Partition, how many partitions? It counts the number of partitions of a set. So first of all, that what do you mean by partition of a set? Partition of a set. So you know this thing, the partition of a set means suppose I am having a set here, any set S. Huh? So partition means you know, I mean very well that you are just okay. You can partition our country into different states. A state you can partition into districts like this. So this each part will be called a block actually. Each part will be called a block. Okay. Each part is called a block here. So this partition of a set is actually this you have to write as union of disjoint subsets. Okay, a partition of S is a collection of disjoint subsets of S whose union is equal to S. Okay, so a partition of S is therefore, let me write down, let S be a non-empty set. S be a non-empty set. So a partition of S is a partition of S is a collection, basically this is a collection or set actually, is a collection of pairwise disjoint subsets, pairwise disjoint, also non-empty subsets. No, I mean need of taking the empty subsets. This will not give anything. Okay. So collection of pairwise disjoint non-empty subsets of S whose union is equal to S. Whose union is equal to S. Okay. This is what I mean. This is what a partition of subset S. Well, I mean if this collection C, this collection says C, okay, let me one more thing that the block I was telling. So here this C collection C, this is actually set of, this is particularly set only, set of subsets of S. So an element of C will be called a block. Okay, an element of C is called a block. This is called a block. This is called a block. Well, this, that means how this C looks like. C is collection of some subsets S1, S2 to Sk, and here each Si is a subset of S, and Si intersection Sj is an empty set, and this is not equal to empty. Si we are taking non-empty set. Okay, not an empty set, and their union, union of Si I from 1 to k, their union will be whole set S. Then we say that this C is a partition. Okay, C is a partition. C is a partition of S. is a partition of S, right? Well, this Stirling number of second kind. Actually, this collection C I have written here that C is a partition of S into K parts. Here K parts I have taken. C is a partition of S into K blocks, into K blocks or K parts, into K blocks. C is a partition of S into K blocks. Well, so this Stirling number, this gives, this number is this Stirling number of second kind. So I'll write down this as the number of partitions of n set. N set means a set with n number of elements. The number of partitions of an n set means a set with cardinality n. You understand, right? A set with n elements. N set means a set with n elements. A set with n elements. That is an n set. So the number of partitions of an n set into k blocks is the Stirling number of second kind. Is the Stirling number of second kind and is denoted by its notation is capital S N K. This is capital S N K, and this small s we shall use for first kind. So this is what the difference. This small s we shall use for first kind, Stirling number of first kind. This is for Stirling number of second kind, that S and K. Well, so tell me that, for example, what will be the value of, say, let me have this, okay, give this example. What will be the value of, say, I'll ask you to find the value of S43. Suppose I'll take S43. What is S43? So here we shall take a set. Okay, we shall take a set, say X is 1, 2. For example, just I am taking any set with n number of elements. Any set with n number of elements. I am taking this set X, that is 4 elements. Here we want to find out n equal to 4 here. Okay, n equal to 4. Therefore, I have taken a set with 4 elements. And partition of X into 3 blocks. Okay, how can you partition this set X into 3 blocks? How can you partition this set S into 3 blocks? That partition of X into 3 blocks. How many are there? How many are there? So how many you can have? You are having 3 blocks, means how can you partition this? This number is 4 only. This number is 4, so there 4 elements are there. So you could do that 2, 1, 1. This is the only way, right? That you want to, break into 3 parts, right? So in this is only one way, I think, that in one part you will have 2 elements. This is block size. These are the block size. So block size will be 2, 1, 1 only into 3 parts, right? We cannot take in any block 3 elements. Total 4 elements are there. So no block can have 3 elements. A block can have at the most 2 elements, right? And all 1 also we cannot take because with this only 3 blocks are there and total 4 elements are there. So therefore, this is only way that block size you can have. Block sizes are 2, 1, 1 only. Fine. So these block sizes are 2, 1, 1, and hence this, how many ways you can do this thing. In one block you are having 2 elements. So once you select these 2 elements, from this set, other 2 are singletons. So they are determined. Other 2 are singletons and they are determined. So therefore, this is exactly 4C2. Do you agree with this? That therefore S43 is equal to 4C2 only. 4 choose 2 only. Do you agree with this?
Yes, ma'am.
Yes, ma'am.
Okay, so this is equal to 6. Do you understand the logic here? One block have to contain 2 elements, and one you select this block containing 2 elements. Other 2 blocks are determined. They are singleton sets. So therefore, the total number will be how many ways you can select this block 2. A block with 2 elements. So therefore, 4. This set is having 4 elements. Out of 4, 2 elements we can select. In 4, choose 2 way, and this is what you answer. Okay. Quickly, I'll tell you another example. This Sterling number. This 4 S42 say. What will be this number? So here that we are partitioning this set into 2 blocks. Okay, so 2 blocks. What will be the block sizes? So block sizes will be either 2, 2. These are the block sizes. What? The block sizes. Here you can have this one, that either 2, 2, or you may have this way, the 3, 1, right? These are the 2 possibilities of the block sizes. So these are the 2 possibilities of the block sizes. So for this, that block sizes 2, 2 say. Block sizes 2, 2. Say for example, I have selected here 1, 2, and then the other one will be 3, 4. Okay, this is partition looks like this. This is one example of such kind of partition. That into 2 blocks, k equal to 2, into 2 blocks, and each block will be of cardinality 2. So therefore, we'll have, tell me how many such partitions you can have. For partitions of X with block sizes 2, 2. With block sizes 2, 2. So now
4C2
you
by
say,
2.
see, look, once I select any one of these blocks, say first block, I'll select the first block. The other block will be determined uniquely, just the complement of this first block. Complement of the first block, it is determined uniquely, right? So here this total number will be what? This 4, C2 if I take 4, okay, 1 minute. 4 choose 2 if I take, then we are counting this twice, right? Do you understand? 4 choose 2 if I take, that's 6. So for this actually, out of this 4 subset, we are selecting 2 subsets. So this, whenever we are selecting this block, say this pair 1, 2, then this 3, 4 is determined uniquely. So this in this selecting 2, when we are selecting 3, 4, then 1, 2 is also determined uniquely. So therefore, we are counting twice, right? We are counting twice. So therefore, you have to divide by 2, and you will have only 3 such. Do you agree with this? It is all right. So we are having, we are having only 3 partitions into that 2 parts of block size 2, 2. Okay, block size is 2, 2. And what about this? Here you are having block size is 3, 1. So if you select any 3 or any 1, it is same. Any 1 say, then the other block is uniquely determined. This is just the complement of this singleton set. So how many ways you select this? I mean block consisting of single element or the other one. So that we do, therefore here this total number here, total number of such partitions you get here is 4. 4 elements are there. And hence this value as 4, 2 is equal to 3 plus 4, that is 7. Right, it is all right. Okay, so this is how, and you investigate one thing. I'll give you this exercise. I mean this I'll write as a theorem. Okay, this gives you recurrence relation of Stirling number of second kind. You tell me how many of you can prove this. Tomorrow I'll check. So here we are taking n and k positive integers. Let n and k be positive integers with n is greater than or equal to k. Then these Stirling numbers satisfy this recurrence relation. S n k is equal to S n minus 1 k minus 1 plus k into S, sorry, here k into S, S of, you write S of n minus 1 k. It is clear to you that S n minus 1 k minus 1 Stirling number S and k into S of n minus 1 k. So this Stirling number of second kind, it actually satisfies this recurrence relation. Okay, you note down, think over this. Why is this true? Today time is over and tomorrow I'll tell you the proof of this. And I'll check how many of you can tell its proof. Tomorrow we'll see it. Okay, that's all for today. Okay then, that's all for today. Bye everybody. Have a nice day. Okay, welcome.
Thank you, ma'am.